Welcome to Algebra 1. In Algebra this year, we are going to be studying a lot about how to use the kind of math that you've been learning throughout your entire math career to do something very specific. What we do in algebra is we represent entire sets of numbers with variables. And then we do math around those variables to find relationships among entire sets of numbers all at once. That's the big thing that's going to set algebra apart from math that you've done before, is we're going to start representing numbers with variables. We're going to start representing equations with functions. We're going to be dealing a lot with equations. We're going to be dealing a lot with expressions. We're going to be dealing with functions later this year. And in order to make sense of all of this, you need to be ready to think abstractly about sets of numbers at a time. Now, this first lesson in algebra, we're not going to get in anything that's that complicated. We're going to build up to that throughout the year. We're going to learn how to use the kinds of math that you've been using, addition, subtraction, multiplication, division, with variables as we go. The very first thing we need to do, though, is something that students sometimes find easy, but I'm going to say for some of you, this is not going to be a super easy lesson, even though it's lesson number 1. And the reason for that is because we're going to be talking about number theory, and number theory is really abstract. Okay, so some of you are going to find this is a super easy lesson. It's really easy for you to put numbers into classifications and categories where they belong. Some are going to find this to be a bit of a challenge, and that's okay. It's okay for you to find this a little bit challenging. Stick with it. It'll make sense after a little bit. One of the words I used a lot in the intro was the word set. And what we're going to do in this first lesson, define a lot of different terms to start. We're going to start by defining the word set. A set is just a collection of objects, a collection of things. For example, a set might be the different textbooks that you have for all of your classes. And then you could list all the different textbooks you have for your classes. That would be a set. In algebra, usually a set refers to a collection of numbers. Okay, there's different kinds of sets. We're going to talk about the different kinds of sets. One kind of set is the empty set. It's a set that has no elements in it. A lot of times we find an empty set when we try to identify something that's in one group and another group. But sometimes we just try to identify one group. Like let's say, for example, in 1 year at Christ Lutheran School, we didn't have any 9th graders. The set of 9th graders at Christ Lutheran School that year would be the empty set. There's nobody I can put in that set. Let's say, for another example, I'm keeping track of the eye color of everybody in 9th grade. And I find that a lot of people have blue eyes, brown eyes, but nobody has green eyes in 9th grade. So if I were to say the set of 9th grade students who have green eyes and there was nobody, then that would be an empty set. It's a set with no elements. Okay, and those exist when we try to define what goes in a set and we have nothing to put in the set. We also could have a finite set. This is the easiest type of set for you to relate to. So this would be like that example I gave earlier of the textbooks that you have for all of your classes. That'd be a finite set because you have a countable number of textbooks. Hey, what about this set? The set of all people living on Earth right now. Is that a finite set? Yes, because right now there is a countable number of people living on the Earth. It's huge. It's a very large number, but it is a countable number. I can put every single person into that set. Okay, so a finite set just has a finite number of elements. It can be a gigantic number of elements, but it's finite. It's countable. What about an infinite set? This would be a set that has an infinite number of elements. These are going to be sets we're dealing with in this lesson. So we're going to talk in just a little bit about all of the counting numbers. 1, 2, 3, 4, 5, 6. Could I ever run out of counting numbers? Is there going to be a number that I reach? Oh, sorry, there's no number next, so you're out of numbers to count with. No. There's an infinite number of numbers. So the set of counting numbers we're going to talk about is an infinite set. In fact, all of the sets that we're going to talk about, these mathematical sets we use to classify numbers, are infinite sets because we have an infinite number of numbers to put into the sets. then lastly, we're just going to talk about set notation. Set notation, and this is not a definition, by the way, that's in your Saxon Algebra book, but it's one that's important because the Saxon Algebra book uses this notation all the time. So I'm going to talk about it. In set notation, elements are written inside squiggly braces, and they're separated. Different elements are separated by commas, okay? Let's take a look at some examples of sets in set notation. This might be the set of eye colors of students in a class. Blue, comma, brown, comma, green, comma, gray, hazel, comma, gray. There are 5 different colors in my set. Notice that I included squiggly braces on the outside and then a comma between each element. This is the mathematical notation for a set. Okay, 5 different things in a set. This is, by the way, a finite set of eye colors. What if I asked everybody what their favorite food was, and these are the answers I got back? So the set of favorite foods of students in one of the grades could be pizza, spaghetti, tacos, steak. Again, squiggly braces around the outside, commas in between. You really need to understand how to write things in set notation. And then we're going to see in a little bit the way I would note the set of all counting numbers. 1, 2, 3, 4, and then an ellipsis, a dot, dot, dot. That shows that the set is going to continue forever. It's an infinite set, but it's going to continue according to the pattern that's already shown there. All right, now let's get into the sets that we use in number theory, the sets into which we're going to classify all real numbers. And I'm just going to show you a big diagram, and we're going to go through the diagram one piece at a time, starting with the center of the diagram. We're going to start at the center down here, the natural numbers, okay? By the way, this is a Venn diagram. A Venn diagram is meant to show relationships between sets of things. So here I have sets of numbers. I'm going to show you the relationship between these sets of numbers. First of all, the natural numbers are also called the counting numbers. They're the numbers that are used to count things. Notice I start counting at 1 and then go to 2, 3, 4. When I'm counting things, like let's say I'm counting sheep as I'm trying to go to bed at night, I'm going to have 1, 2, 3, 4, not 4.5. I don't count halves of things. I count whole things. A half a sheep would terrify me and I'd have a nightmare. But instead, I'm going to count individual whole sheep, 5, 6, 7, 8, 9, 10. Those are the natural numbers used to count things. No decimals, no fractions involved. And the number 0 is not a part of the natural number set because we don't start counting at 0. I guess unless you're a computer programmer maybe, but you don't have to know that. Instead, you start counting at 1. All right, let's go to the next level up, the whole numbers. The whole numbers are the natural numbers, but this set of numbers also includes 0. So these sets are very much overlapping sets in that natural numbers are entirely contained within the whole numbers. The only number in the set of whole numbers that's not a natural number is 0. So the set of whole numbers is a little bit bigger than just the set of natural numbers. Natural numbers is a little more restrictive. Then I'm going to go up one more level to the integers. Integers include all of the whole numbers, starting with 0, and then 1, 2, 3, 4, 5, 6, 7, 8, on and on, and the opposites of the natural numbers. We say that 0 doesn't really have an opposite because it's 0. I mean, what's negative 0? It's just the same thing as regular 0. So that's why we don't say the opposites of the whole numbers. We say the opposites of the natural numbers because the natural numbers do have opposites. So I would start at negative infinity, okay? And I would count up negative, blah, 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 and then it gets a negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. Notice I have an ellipsis over here. So I'm starting at negative infinity and counting up to 0. And then I just keep going past 0 and then up to positive infinity. That would be the set of integers as long as they are whole numbers or the opposites of natural numbers, okay? So I'm not including fractions and decimals yet. That's actually the next group of numbers. Rational numbers include all of the integers, which includes all of the whole numbers, which includes all of the natural numbers already, okay? So rational numbers is a much more inclusive group because it includes everything so far and any other numbers that can be written as a ratio, rational ratio. You see that word in there? Ratio just means like a fraction in the form a over b, where a and b are both integers. Okay, so they have to be like whole numbers or their opposites, right? And b, the number on the bottom of the fraction, can't be 0. So any of the integers can be represented as a fraction if you just put it over 1, right? -4 over 1 is still -4. 0 over 1 is 0. 3 over 1 is 3. Therefore, all of the integers are rational numbers, but so are the numbers in between the integers, like 1/2, 2/3, 2 over 229, right? So there's a lot of numbers in between the integers. Those are included in rational numbers. That's why I can't just make a list of them, because there's actually an infinite number of numbers between 0 and 1 that would be considered rational numbers. Hey, does that include all of the numbers? By the way, I'm just going to mention this. Another way to say this, and it says this in our Saxon math book, so you should know this too. Another way to define the rational numbers is if you write them as decimals, they're either going to be repeating or terminating decimals. So let's just take a look at the examples here. 1/2 and -2/3 are obviously rational numbers because they're written in fractional form. But what about 0.3 repeating? Well, 0.3 repeating, as you'll learn in some of the homework problems when you go back to the skills bank in your textbook, there's a way that you can write 0.3 repeating as a fraction. It's a clever way to do it according to your Saxon math book. Because you can write it as a fraction, repeating decimals are rational numbers. So are terminating decimals. 0.125 ends after the 5. That is a rational number because it can be written as a fraction. In fact, I could write that one as 125 over 1,000 as a fraction. Any decimal that terminates, I could do that. I could just write it as a fraction based on where its decimal place ends. All right, what about the irrational numbers? Are there numbers in between rational numbers? Yes, there are some numbers on the number line in between the fractional numbers that you can express as fractions. We call those irrational numbers. These are ones that have radicals in them, or the number pi, or another constant that is non-terminating, non-repeating. Okay, so pi you probably recognize as 3.14, but that's an estimation of pi. Actually, pi has an infinite number of digits that never end and never repeat. So and remember, pi is just the ratio. Let's see, so 2 pi r is the circumference of a circle. That relationship relates the distance outside of a circle to its radius or its diameter. Pi, instead of 2 pi r, we could do pi times the diameter equals the circumference of a circle. So it's just this number that we use to relate the distance across a circle to the distance around a circle. And that is a non-terminating, non-repeating decimal. Just like all of these square roots, the square root of 2, cube root of 5, anything with a radical in it like that is going to be non-terminating, non-repeating. Unless you see, like if it's a square root of 4 and it obviously terminates, the square root of 4 is just 2. But if it's not an easy square root like that, it's going to be an irrational number. Irrational numbers are not rational numbers. And the set of irrational numbers does not include integers, whole numbers, or natural numbers. It's just kind of its own set off by itself. But there is another set, a bigger set of numbers that includes all of the numbers we've talked about so far, rational numbers and irrational numbers, and that is the set of real numbers. Real numbers is defined as the set of all rational and irrational numbers.